The SST K-omega model is one of the most popular turbulence models in use today. SST stands for shear stress transport, and what the model does is it combines positive features of the K-epsilon and K-omega models into a single hybrid model. The K-omega model performs better than K-epsilon models in boundary layer flows, but the K-omega model is also overly sensitive to the free stream value of omega, which is what we need for boundary conditions, while the K-epsilon model doesn't have this sensitivity. So the way the model works is by blending the K-epsilon and K-omega models so that the SST model functions like the K-omega model close to the wall and the K-epsilon model in the free stream. The SST model is a good compromise between K-epsilon models and the standard K-omega model, and it's been shown to have a significant advantage over any of the K-epsilon models for predicting flow separation and heat transfer, and so it should be the preferred choice for those kinds of applications. However, when the flow is not dominated by boundary layer turbulence, such as free shear flows or flows with strong swirl, it may not have as many advantages as it does in boundary layer flows. Other RANS models available in Fluent include the RNG K-epsilon model and Reynolds stress models. The RNG model takes its name from renormalization group theory, which is used to determine the model constants. Compared to the standard K-epsilon model, the advantages of RNG are very similar to the advantages of the realizable K-epsilon model, so we typically recommend using the realizable K-epsilon model. On an earlier slide, it was mentioned that Reynolds stress models solve transport equations for the individual Reynolds stresses to close the RANS equations instead of solving for an eddy viscosity. So what this means is in a three-dimensional calculation, then compared to an eddy viscosity model like K-epsilon or K-omega type of models, where you have 2 additional transport equations, with the Reynolds stress model you have 7 additional transport equations. This means the model is much more computationally expensive than an eddy viscosity model, and Reynolds stress models are also generally very difficult to converge. Because of this, the Reynolds stress modeling is typically used only in flows where it's already known that eddy viscosity models are going to fail, and Reynolds stress models are guaranteed to give better accuracy. A particular class of flows like this are flows which involve strong swirl, or where strong swirl is a predominant flow feature. And there's a good example of this if you look in the appendix and see the case study of the flow in the cyclone.